big, scary, pure mathematical object that anybody who does anything applied never really wants to touch. But in recent years, we've found ways to do it, and it's actually a really nice way to represent our data. When do we want to use sheaves though? Basically when we're going from a local perspective to a global perspective. So when we know something locally, how to do some calculations, but then we want to recover something from a big grand scale. So let's have a couple of examples. So maybe I'm working on a manifold and I know what some structure looks like locally, but I want to piece together and see how this extends to the world around it. This is something that's built in for sheaves. Alternatively, based on a really nice paper, and this paper, we can also look at the global to local perspective or vice versa. And let's imagine we're looking at forces in a building structure. We know locally how the forces impact each other based on the tension of different bars connecting things. And we know what structures we want to get. And sheaves gives us a way to go between these different worlds. Okay, so let's talk about what actually is a sheaf. And actually we're going to talk about cellular sheaves because they're a lot easier to work with, and they're sort of the things we're working with when we actually have data. So to do this, take your favorite cell complex. I've chosen a random cubical complex here, but if you don't like cubical complexes, you can easily choose simplicial complexes or anything else. And we're going to do two things. So first of all, we're going to assign an object to every cell. Okay, so in this case, I have assigned a vector space to every cell because I love working with vector spaces. So that's the first thing that a sheaf requires. The next thing that it requires is we need to assign a transformation. We take it from every face of a cell to the cell itself. Okay, so here, for example, I have a transformation from every vertex to its adjacent edges. So I have a map here, for instance, from my vector space F6, my 6-dimensional vector space attributed to this vertex. And I have maps going horizontally and vertically to the adjacent edges and their associated vector spaces. And for every 2-dimensional cell, I have a map going from the vector space on each edge to the face itself. And I do this for every cell in my complex, and I need to make sure that they satisfy commutativity and everything like that. But it's a really simple structure in the end. We just have an object for each cell and a transformation for, between any pair of cells. Okay, now that we have a sheaf, let's talk about the 3 certainties of life. That's death, taxes, and co means things go the other way. So when we have a sheaf, we also have a notion of a co-sheaf where things go the other way. So if we have a sheaf, what now is a co-sheaf? Well, it's the same build-up. We take our favorite cell complex, we still assign an object to every cell, so I'm still assigning a vector space to every cell. The only difference now is when co means things go the other way, all our maps go the other way. So we assign a transformation from each cell to each of its faces. Okay, so when I have a co-sheaf, I have exactly the same thing, except now my maps go from higher dimensions down to lower dimensions. So from every 2 cell to its boundary edges, and from every edge to its boundary vertices. Okay, so say now you have your sheaf, like this example over here with this cubical complex. What do you want to do with it? What sort of things can you do with it? Well, the first example is what local features of your data would persist everywhere. So over here, what we're representing by these vector spaces and these transformations is some local data centered around each cell, and these maps tell us how to glue it together. So let's take a more local example here. I have an edge with two vertices, each with a two-dimensional vector space, and I have these two matrix transformations attached to it. Now, if I take the vector space of two elements, and I take the element 1, 1 on the left vertex, this maps to 0, and so this feature that appears in my data here disappears once I push through my complex. So maybe we want to look at that and the cases where this does or doesn't happen. Another example of, well, when we're pushing through our complex here, that's sort of a diffusion process, and so sheaves and cosheaves have been used to track sort of diffusion equations previously, quite successfully at that. And maybe we want faster algorithms, we want faster implementation of our data, and this idea of breaking up into small parts, divide and conquer, and then glue them back together gives us really great examples of parallelizable algorithms, which will hopefully speed up our computation time. So we've seen that sheaves appear very naturally, and we can use them in a lot of contexts, and there's a lot of intuition behind them, but they also have a rich algebraic structure behind them too, which is why they're so great to use. So some examples of this, we have a notion of cohomology of sheaves, or homology of cosheaves. And this cohomology or homology, whichever direction you're going, tends to tell you when our local data features do not extend globally. And it's very similar to our usual notion of homology or cohomology. So let's take this cubical complex as an example here, and let's look at the one-dimensional co-boundary matrix. Now, usually when we do the co-boundary matrix, we're defining our maps possibly with some sort of orientation from our one-dimensional vector space over our edge to the one-dimensional vector space over each of our two cells, and doing this for all of them. All that changes when we have sheaves or cosheaves is we're factoring in that maybe our vector space is not one-dimensional, and we're factoring in that maybe our maps aren't the identity maps. So in this case, if we want to map from our edges to our two cell, we need to factor in the horizontal map, the vertical maps that map from the edges to the two cell, and also the fact that this edge has no two cell attached to it. We also have this notion of sheaf morphisms, which gives us a way to compare different data. So if I have two different sheaves and I want to compare them, I have a notion to do this, and this can help me give some stability results, for example. And there's many more. Personally, I look at things called bi-sheaves, which add extra structure above sheaves and co-sheaves, but there's many different ways to look at that within data. And to finish up, I'll run through a few examples of papers that you can find on the topic.